And thank you very much to the organizers and to everyone who's given us such great hospitality. I'm Bart Massey. I want to talk to you today, assuming this works, there we go, about a completely non-technical topic. We've had so many amazing technical talks this morning, and I'm going to go completely the other direction and talk to you today about a sort of a strategic thing, which is about Rust and the university situation, because universities are, I think, important in ways to a language and to the future of a language in ways that a lot of people maybe don't quite appreciate. And so I want to talk a little bit about that, and I want to talk a little bit about how we get there. So that's my thing. I'm here representing my institution, Portland State University, but also representing the Rust Edu project. I'll talk more about that in a bit. So yeah, oops. And I'll go the other way. One of these will work. There we go. So universities and Rust have a ton to offer each other. I think this is a place that can be a focal point of Rust and a place where we can provide things to the rest of the ecosystem. But it's not as much of a slam dunk as you would think at first glance. And what I want to talk about today, based on many years of experience and putting on my old man hat, I guess really many decades of experience in higher education and in programming languages, is how we get there, how we get to the point where the universities and the Rust community are maximally co-productive. They work well together. So what is it that Rust offers universities? Well, I think it's pretty clear, to me at least, and I hope to everybody in the room, that Rust is the future of systems programming. That's a good place to start. I think it's pretty hard to argue otherwise in current year. And that means that if the universities want to join the future of systems programming, they really need to figure out how they're going to handle Rust for that in that application. Now, obviously, Rust is more than just a systems programming language. That's a nice starting point, but it isn't where we stop. The other thing that Rust offers universities is a sort of programming language paradigm that's underexplored, and that's the paradigm of sort of maximizing static analysis, doing the most at compile time that we can figure out how to do. One of the premises of Rust, which goes beyond just borrow check and how do we make sure that things are memory safe, is this idea that anything we can figure out at compile time, we should figure it out at compile time rather than waiting to runtime to find out about it. And that's a really powerful thing. Other languages have obviously worked in this direction. There are languages that go very much more in this direction. But in terms of practical systems languages, we're in a pretty special place there. And like I say, it's not just the borrow checker, it's also the type checker and a whole bunch of other machinery that we try to do these analyses. And I think the analyses get cleverer every year, and that's awesome. So what does that give us? Well, it gives us efficiency, which is very important to people. It gives us safety, which is very important to people. But it also gives us sort of good designs. The Rust compiler encourages good data and program designs by doing these static analyses that point out problems with your design and encouraging you to find better ways. And at the end of the day, it's just a good general purpose language. There are very few application domains right now, from very high up to very low down, where I haven't tried to write at least a little Rust code, and in every one of those ones I have, I've had a really, really good experience, and I think the experience gets better every year. So given all those things, it sounds like something universities should and would really want to have. It seems like, yeah, this is an easy sell. Let's talk a little bit about that. Oh, first of all, I should qualify myself a little bit. I've taught about 300 students Rust over about 9 offerings in the past 5 years. I taught a Rust Web and Rust Assembly course with a co-instructor this summer. So I have some experience with that. I also have been doing university education for a long time. 30 years is really an underestimate. I was, before my 25 years or so as a professor at Portland State. I was a tenured graduate student, and you get to be a tenured graduate student, of course, by spending your 10th year in graduate school. So really, I've been hanging around the universities my entire life. And so what I want to talk about is how to get Rust into universities. And like I say, given the previous slide, why is this a problem? Well, we'll talk. And that's in the West, but also worldwide. I should really say that while I'm learning as fast as I can, I know about Western university systems. If what I say doesn't apply to your university system, please tell me. I'm always eager to learn. I don't claim to be an expert on any of this, but especially on stuff outside the West. And again, this is not a technical talk. There are very few provable or checkable things here. It's opinion. I feel like I've earned those opinions, but I want to make it clear that that's what I got for you today. So I want to start with some history. It's fun to have history, especially when you've lived through it. In the 1970s, really, AT&T, the phone company in the US, developed this thing, very famously, called Unix. And one of the things they started doing was sharing the source code with universities under a license. It wasn't open source by any means. It was very much shared source, and each university had to get an individual license, but they did. And they did it really mostly just because they could and they thought it would be interesting. At the time, people were running proprietary operating systems on basically all the hardware, old school proprietary operating systems. The target of Unix was the PDP-11, a Digital Equipment Corporation DEC system. And before that, I guess the PDP-8. The point is that these were all running DEC proprietary operating systems, and this was a way for universities to get an alternative to that was smaller and simpler and easier to understand, cleaner, and it was a way to give students a look inside the source code of a real operating system. It really took off. You may have noticed that we're still using Unix how many decades later, right? Because it turned out to be a really, really powerful thing that AT&T did. So, by the 1980s, I was in school in the early 80s, I walked in and we had a thing running Unix, PDP-11 running Unix at my university. And that was my first exposure to real computing. I'm a microcomputer kid from the 1970s, and so this was a real revelation to me to see a real operating system with real source code. And it turned out everybody wanted this. It was very, very timely, very, very well placed, and I would argue that the university placement was not only a big reason why Unix took over the world, as the people who graduated having had this went out and did things, it's also a real foundational thing of open source itself. You got to remember that the earliest open source licenses were MIT and Berkeley's. It's not a coincidence that they were universities, and Berkeley's in particular was applied to the source code for their Unix fork that they did. It didn't start as a fork, but it finished as one. Huge success. And when you have a huge success like that, when you've done something that powerful, people notice. And what followed was several decades of people trying to repeat that success, right? They're like, oh, this is how you get your thing to be cool. You give it to university students, and then they go and do the thing, and that's what triggers the revolution. Well, yeah, right? I mean, there's more efforts than I've got on this slide. In the interest of time, I thought I'd keep it to 3. Sort of in the 1980s, when Apple came out with the Macintosh, my university, there again, I was still an undergraduate, they piled Macintoshes onto our campus, trying to get us to be excited about the 128K Macintosh, the 1984 model. And, it was interesting because, yeah, it probably had an impact, but it certainly didn't succeed in the same way Unix did. There's a bunch of reasons for that. One of them was that the 128K Mac was not only a proprietary system that you really, even though they gave us good documentation for its APIs, it still was, opaque inside. The other reason another reason is that it was not bootstrappable. It was too small. It couldn't compile. You couldn't compile Mac programs on the 128K Mac. You had to use the Apple Lisa, which was a $10,000 debacle, which deserves its whole own talk with all kinds of interesting lessons. So, mixed success. I would say that they definitely had an impact in the universities, and it definitely translated into impact in the real world, but not as big a deal. There again, Linux, right? We go back to the Unix world, and Unix is kind of cooked along as a university thing. And this guy does this thing where he's like, well, I'm going to write my own Unix, and me and my friends are going to write our own Unix. And one of the things that happened there is that very quickly it reflected back into the university space. It was because it was open source, because it was, there again, a small, simple, transparent system of the kind that that Unix had grown not to be in some ways, and for a whole bunch of other reasons. The synergy between Linux and university is very strong, and it worked out well. And we could talk about Java, which has a story that was not a very successful story in universities in some ways. We could talk about a whole bunch of other things. The Next. Probably most of you don't remember the Next Cube. So yeah, there's been a lot of effort to do this thing because it was so cool when it happened the first time. And here we are. We've got our own thing, Rust. And I would like to claim those same benefits for Rust. So let's talk about what makes it hard. Why did after that first time things not work so well? CS departments are resistant to technology. That's a very strange statement. Let me qualify it and explain what I mean by that. The computer science departments I have experience with, and certainly my own, do not want to visualize themselves as primarily industry training grounds in current industry technologies. They don't want to be just programmer training schools in a CS department. And that's a little bit dishonest. At my institution, like 95% of undergraduates go directly into industry, but there's a lot of aspiration to serve the other 5% well. On a more fair assessment, there's also a feeling that I agree with, that if you teach today's technology, you're out of date in 3 years. We hope to give you principles and ideas and experiences that will last you decades, not moments. And so if we're gonna get our thing, Rust in this case, into universities, we're going to have to overcome the perception that it's just another programming language tech, like literally 50, right? We're in a Cambrian explosion, right, of languages, of programming languages. After a very long period in which we didn't have much language innovation, the last 10 years have been just crazy, right? And if we're perceived as just another one of those new languages, we're absolutely doomed. The universities have no chance in that. So we have to present ourselves as more than that. That's absolutely essential. And that's the first thing we have to figure out is how do we do that? And I think there's two approaches I'm really going to advocate today. One of them is to say, no, we're not trying to get you to teach Rust for Rust's sake. We're trying to get you to teach Rust and use Rust in the classes where it's the natural language of application. And there again, I think that starts with system stuff. That starts with your operating systems class. It starts with your embedded programming class, if you have one, right? It starts in places where it's hard to avoid that the current languages are not serving us so well. And it's hard to avoid seeing what a better language can do for improving education that isn't the language for the language's sake, but the language because it's the right tool for learning this other stuff. So that's strategy one, and I think it's really, really super important to do. And I'll throw in with that, as part of strategy one, security is a big deal right now. Certainly, academic CS departments have been forced to pay attention to the security problem. And when you're paying attention to the security problem while still trying to produce practical programs, there again, you say, well, we're not teaching Rust for Rust's sake. We're teaching Rust because it's the secure applications programming language for security, and will make things secure. So there's that. And then the other thing is to really argue that no. Rust isn't just another programming language, right? It isn't just the next iteration of another mixed imperative functional language. It's got a whole bunch of good ideas beyond the core idea, and we shouldn't underemphasize the core idea. One of the things I've been saying to people lately, and I've gotten a lot of nods yes, is this idea that part of the reason that you can get away with teaching Haskell in every university in the US is because you're not teaching Haskell, you're teaching a paradigm, you're teaching functional programming. And it's, while Haskell is for today, maybe, functional programming is a thing that'll last you 30 years. We need a name for what Rust is, right? And what Rust does. And, we've talked in academia about names like, region analysis and static GC and blah, blah. We need a name for the core paradigm that Rust is. I was just pushing on an earlier slide maximum static analysis. So call it a static analysis language or something like that. I don't know. Maybe one of you will come up with the right term. But we need to explain that there's some ideas here that are new and yet fundamental. There are things we aren't teaching right now that we need to teach everybody. And, so what do we got beyond memory safety? Well, that's already a lot. We've got a lot of efficiency things for functional and concurrent programming, right? We've really shown more than any language before us, I think, how you can have a practical language with sort of learnable primitives that accomplishes new levels of efficiency, right? Our weird closures are weird closures, but they're weirdly cool because they let you use closures in places where before you'd be like, nah, I can't afford the garbage collector, I can't afford the runtime overhead of dereferencing this stuff. Sorry, I promised it wouldn't be a technical talk, and here I am. The other one is, sort of software engineering is a real thing. I was hired actually as a faculty member to teach not just computer science, but to teach into our software engineering master's program. And in the area of software engineering, I think Rust brings a whole bunch of ideas to the table that are novel enough that they deserve to be their own thing. We really need to talk about how our build system is more than just yet another build system, right? Because it really is more than just yet another build system. It's the most loved build system this year for a reason, right? And it isn't just because we got some of the details right, it's because we took a different approach in a lot of ways to what people were doing. Our documentation and testing stuff is kind of special. And so the more we can present to the universities that that's what we're trying to do, the more we're going to be successful in getting things in there. And overcome some of this pushback that I was talking about. See, the problem here is probably as old as computer science, but certainly as old as how long I've been doing computer science, is the programming language war. Every 3, 4, 5 years, somebody's like, we gotta stop teaching language X, and really the future is language Y, and we've got to adopt language Y for everything, right? It was first, we got to stop teaching Pascal and start teaching C. We've got to stop teaching C and start teaching C++. We got to stop teaching C++ and start teaching Java. But along the way, there was a million forks that didn't succeed, right? Throughout the whole 90s to today, we've got to stop teaching all these things and do everything in Scheme. Scheme is the only way. It goes over and over and over like this, and every faculty member is tired of this argument. Every university is tired of this argument, and if it looks like you're in the programming wars, then you're doomed. You won't get anywhere. So, everybody has their own idea of what the best first and second language will be, And because everybody's tired of it, and because the languages we use now, which is typically Python and C or C++, in the US, because those languages are kind of good enough to get by with, there's a lot of inertia. That's a good place to get to eventually, but it's not where we start. If we start there, we'll probably run into the inertia. That's part of why I'm advocating so much getting Rust in the back door through applied courses, is because those are easy to change. An applied course is typically written, structured very much by the professor, not the department. It's typically flexible in its content because it has to adapt to new applications and things. And once you've seen success, once you've seen effective use in that setting, then it's much easier for the department to talk about the horrible task. In our department, we have a full year of very extensive C++ curriculum. It's a big, big part of our instruction, really more than that if you count everything up. And to change all that is huge. And there's no way I can sell them on changing it until I've demonstrated that it's worth changing. And I think most departments are in the same position. So that's where we start. There's the Rust is hard to learn argument, which we've talked at the workshop a few days ago, and we should talk today about. First of all, you should see my workshop talk about how much better the learning resources have got. We've talked about the sharp edges we've shaved off the language in the compiler. Rust is way more available to university students than it's been before. I mean, it's certainly less hard than Haskell, which is very successful in universities in spite of its difficulties. So we really have a place that we can be. So what's in it for you? All you people aren't university professors, mostly, I think. Are there any university professors in the room? No, one. Yeah, there we go. So for you, hopefully you're on board. For everybody else, what's in it for you? Well, I think the university community has things to offer Rust in terms of programming language research and the like. And if you can engage us, we will help make your language better. We'll join you in making the language better. And we really are, to some extent, in spite of all our denials, an industry training program. I would rather have us training Rust people to build a larger Rust community. And that's something we can do if you help us get started with it. So I'm here on behalf of Rust Edu. The URL is up there. The Zulip URL is up there. FutureWay, a year or more ago, generously funded us to try to get Rust into university curricula across the world. And develop course materials and tools. I would love to have any and all of your support. I think we'll get there. I don't think there's any doubt. Rust will become the university of language of the future, but we need to work hard and we need to have patience because it is going to take a while and it is going to be difficult. But I think it's really, really a journey worth taking, and I hope you'll all join me on it. So that's that.
And I want to have a disclaimer that I never taken a formal programming class, so my question may be a bit naive. But why do you think that universities teach C and C++ now? Do you think, when you say systems programming, what do you mean by that? Because there's a couple different ways that you could approach it. Is it that they want to teach memory handling and the proper way to do that? Because is Rust the right replacement because we abstract it all away, then handles everything. But in C and C++, you have to do it yourself, and you can do it wrong. So yeah, why do you think C and C++? Is it? The other option is just because it's the loose thing.
No, that's a great question. And yeah, a lot of it is inertia, right? In our program, once we've taught everybody C++ for a long time, we have a systems programming course that's C++. We have an operating systems class where they actually build an operating system in C. And we have other courses that use that as their platform. And so it's partly just inertia. It's partly just there's a lot of good materials out there. There's a lot of good tools. But I think to answer your question about why is Rust better here, shouldn't we be bare metal? I mean, honestly, you could make an argument that it should all be an assembly where you really understand what's going on. And the trick is finding the right abstraction point, right? And the right thing with Rust, and the reason I would prefer to use Rust for the systems programming course I've taught or for the embedded programming course I've taught or whatever, is because as a student, so there's this thing we've been talking about a lot around the conference in the hallway track of you find out about your problems with your Rust program at compile time. Somebody else finds out about the problems with your C program weeks or years later. And in a learning situation, when you're trying to understand whether what you've done is right and that sort of thing, that's really, really bad. I mean, the consequences of making bugs in your C operating system you're writing are just so grim that, to me, having a little layer of abstraction that stops that is fine. And one of the things I like about Rust is we don't really hide things very much, right? I mean, absolutely, the mallocs and frees are replaced by compiler inserted operations, but we really can think of it like that, right? It isn't like we have to explain how a garbage collector works. It's, over here it's going to allocate memory because you asked it to, and over here it can see that you don't use it anymore, so there'll be a free inserted. You can't see it, but it'll got released. It isn't that hard to explain. It doesn't get in the way that much. And the unsafe subset, is a thing you can use in teaching in small chunks. And this idea of building unsafe things with safe abstractions is a really, really powerful idea, and there's just nothing like that in C++. Is that a good answer? Yeah, Will Crichton at wherever he is, Brown, I guess these days, and Cyrus Omar at University of Michigan have both worked on some tooling around this stuff that's very, very cool. And I agree, that would really help the educational experience. Now, the counter argument is that the tooling for C and C++ for statically detecting all kinds of bugs has gotten better and better. It's certainly not like it was when I was a boy and the compiler wouldn't tell you anything. So I think there's some convergence here, but I feel like, if you have to pick the one that's forward-looking rather than backward-looking. Sorry, that was a very long answer.
Rust is kind of the only ownership-oriented language other than, there's a few new ones that are being experimented with, but, is our best shot pointing out that there are several other ownership-oriented languages, or does there need to be a production-capable one?
Yeah, I think this is...
More
Right, I think this is why I suggested this is the second thing, is because I think it will take time. Part of what's happened is there's this weird split that's about 15, 20 years old now between the programming language community and the software engineering community, where all the programming language community went off and did programming languages things, and all the software engineering people went off and did software engineering things, and they didn't talk to each other very well. Part of the reason Haskell has become so popular and functional programming has become so popular is because it was a thing that was owned by the programming languages side of the community, which is a very academic place, right? Part of the reason it's more difficult for Rust is because it was owned by the software development side of the community, which is not so much of an academic place. I think that's changing. I think the kind of research we were just talking about, is the way in, is to get to the point where the programming language people are comfortable with saying, oh yeah, I got a grant to do programming languages stuff around Rust, which right now, it's tough.
Professor, I have a question. Why Rust can replace C or C++ in the future? Because in Chinese universities, C is their first class when they enter in the university. And I had worked 2 years, but I still think C is very hard to learn.
Yes.
Yeah. And as I know, Rust is much more difficult than C. So I want to know why it can't.
And I'm gonna, in a very friendly way, and acknowledging that it may not be the minority opinion yet, say no, I think actually Rust is maybe even easier to learn than C. But that's very new, first of all. 2 years ago, 3 years ago, I probably wouldn't have made that argument. The Rust has gotten a lot easier to learn because of way better materials, because of big improvements to the language. And the problem with C, like I say, is that the learning curve is dominated by making mistakes. It's a language in which it's really easy to write code and get it to compile, and even compile without warnings, and then it does a thing. That is really discouraging to people starting out. One of the things we've noticed at my university is that people from underrepresented groups, women, minorities, that kind of thing, people disadvantaged, drop out disproportionately at the level where they encounter C because they believe they must be dumb. Because, I must be dumb because this is really hard and all these people around me don't seem to find it so hard, whereas the usual posers are like, oh yeah, this is super easy. And they're making all the same bugs, but because it's hard to see the bugs, one group feels overconfident and the other group feels underconfident, and it's very, very sad. So, I'm really happy with things that help people understand when they're making mistakes and then quickly correct those mistakes so that the right thing happens. Thank you.